All right. All right, what we're going to do today is we're going to finish off capacitors, and then after that, we'll, if there is enough time or desire, I'll show you test one from the summer. Test one is currently available on Blackboard, so if you want to get it while the lecture is progressing, that's okay, or that's good. More will be coming soon. Also, other announcements, no tutorial on Friday. Videos will be available today, hopefully. So let's get started. So today we're talking about capacitors and how they behave. Capacitors, if you want to build one, the capacitance is related to epsilon naught A over D, where A is the area of any of the plates and D is the separation between the plates, and then epsilon naught is a constant that will be listed in the page of constants. In fact, I shall refer to it now because I don't remember it. 8.85 times 10 to the negative 12 c squared newtons meters squared. Now what we're going to do initially is we're going to talk about series and parallel capacitors. When we have a capacitor that charges, when capacitors charge equal, I don't know what that was, equal magnitudes of Q build up on each of the plates. So when these capacitors say, so this is what we're going to initially talk about first. Not parallel, series. God, it's 8:05 in the morning. We need to be very forgiving at the moment. Exactly. Equal amounts of charge builds up on the capacitor. So initially there's no charge on any of them, but with a long amount of time, equal amounts of charge will build up. And that's because remember when we were doing electrostatics, and if you have something like one object that has an excess of charge or a deficit of charge, when you don't affect it with anything, like another object that's charged, it will reach an equilibrium. And so when this battery has fully charged the capacitor, there are equal amounts of charge on each of the plates. And if there weren't, the battery has not effectively charged the circuit, so it would continue to build up charge until it reached an equilibrium. So for capacitor plates that are charged, they have to reach positive Q and negative Q. For these series capacitors, what ends up happening is that the battery has voltage V, and then what ends up happening here is the capacitor will develop charges on each of these, and then the magnitude of those capacitors will once again be positive Q and negative Q. So effectively, this region in here gets induced, or it is induced charge, and then these are because of the battery and affects everything else. So when you have capacitor plates that are in series, just like you would have one capacitor plate effectively in series with itself with the battery, they each develop a charge of positive Q. Now in our circuit, if we were to sit here and have potential difference measurements made,
are all of these supposed to be positive?
no, positive, negative, positive, negative. What do you mean by all positive?
I thought that was a positive.
No, this one and that one are negative Q. So if you took your voltmeter and you measured the potential differences across each of these, and actually more to the point, this one would be the V of the battery, and then this would be when you have two capacitors in series, you could put your probes of the voltmeter on this side, measuring the potential difference just across that capacitor, and the potential difference across that capacitor. And then you could also measure the potential difference across this set of capacitors. So the question now is, if you've got, just so that people feel they're not really safe if they're in beyond the front row, what is the equivalent voltage of this circuit expressed as other values on the board? What is delta V equivalent? No. You did kind of say it as a question, so I'm not exactly accepting either the attitude or the correctness. This would be wrong and a question. One last shot, then I move over. V. Accurate, but that's not the point. You're not allowed to use V. Give me another value. It's obvious. Is what? No. Thank you for playing. It's the, and you didn't look at me, you just kind of went, oh, this is some of the two. Actually, with the attitude of, I'm not even going to give you the dignity of looking at you, I'm just going to stare away and cite the answer on my own. Delta V equivalent is the sum of delta V1 and delta V2. If that was the midpoint, and this is delta V1, and that is delta V2, then the sum is delta V equivalent. Obvious. Now none of you are safe. In my class, the only person to do puns or jokes are me, unless explicitly stated by me. But that doesn't change the fact that it was still funny. Thank you. Now for delta V1 and delta V2 and delta V equivalent, there is a relationship that we have whereas QV, and really this is Q delta V, these are kind of interchangeable. Or actually, I'm writing this the wrong way. Q is equal to CV, that the charge built up on the plates is the capacitance times the potential difference. Or Q divided by C is equal to delta V. So now, what I'm going to do is delta V1 becomes Q1 over C1. Delta V2 becomes Q2 over C2. And delta V equivalent is Q equivalent over C equivalent. And what we know about capacitor plates in series is that the charge on each of the plates are all equal to each other. So Q1 is equal to Q2, which is equal to Q equivalent. All of those will be the same charge. Otherwise, there will be a redistribution of charge. Yes?
Oh, wait, no. That's a Q. Q equals CV and then Q equals C delta V.
Yeah.
Okay.
A lot of times, potential difference in voltage is still, I run around, I make no, they can be different and they can be the same.
Your Q's look like twos.
I thought it was two. That's not.
Oh, now we're getting judgmental of the professor's handwriting. I'll show you some wonderful examples of yours next time. Yes?
Okay, so in this circuit,
Oh, we're being extra, I know.
so
Yeah.
this circuit V is V like that.
Yeah, so you could write it like this.
That means like the voltage, the total voltage change is V equivalent to the battery, right?
For these, delta V1 and delta V2, it's the potential drop across capacitor 2 and the potential drop across capacitor 1. So delta V1 is, now good question, is it necessary that delta V1 equal delta V2? Is it required? No, says the person 2 rows behind you, and she nods her head correctly. It isn't required that delta V1 equal delta V2. Just like if I had 2 resistors, hooked up to a battery, if they were equal resistors, the potential difference across each would be equal. But if I have a little itty bitty resistor sitting next to a mega ohm resistor, the potential differences across each would be vastly different. So if the capacitors were the same, identical, then there would be potential differences. The potential differences would be different. Kind of meta. Does that answer the question?
So eventually, on either side of the battery, like from positive terminal, negative terminal, the net change would be just voltage of the battery.
Eventually, I think what you're asking, delta V equivalent for this circuit would be equal to the battery strength.
Yes.
Okay. When I wrote this is kind of a general term. I've seen books use this. I've seen books use this. I'm trying to make you familiar with both of them. They're identical as far as I'm concerned. Now, because all the Q's are the same, they drop out. And what we're left with is the equivalent capacitance equation. So if you had a 5 microfarad capacitor in series with a 10 microfarad capacitor, the equivalent capacitance is 1 over 5 plus 1 over 10 inverted. The micro I just pull out and I plop it back in when it suits me. So it would be 3.3 repeating microfarads. If you're adding capacitors with the same scientific ending, microfarads to microfarads, nanofarads to nanofarads, mega ohms to mega ohms, you could just pull out the mega ohm and save it till the end and put it right back on. Now for capacitors in parallel, you get this. So obviously these capacitors are in parallel. In fact, I'm going to write it a little bit bigger so that we can have it bigger on the screen and I have more space to draw. So the equivalent potential difference is there. The potential difference across 2 is there. The potential difference across 1 is there. And so this is our equivalent capacitance, which you could also say for the potential difference is like this. So what do we know about the potential differences across 1, 2, and the equivalent? What is the obvious, immediate observation? Yes?
Delta V equivalent equals the sum of things.
You're saying that that delta equivalent is equal to the sum of the differences?
Yes.
So you're saying that delta VEQ is equal to delta V1 plus delta V2?
Yes.
All right, 2 points. 1, very good. Your attitude was completely correct. Point 2, your answer was completely wrong. Let me ask you a question. Is the potential difference here the same as the potential difference there, or the potential there equal to the potential there? Yes. Why? Does it pass through a resistor?
No.
Does it pass through a battery? So those 2 points are of equivalent potential. So all of those are of that potential. Is this from there to there, do I go through a resistor? No. Do I go through a battery? No. So that potential is the same. So if the potential there is the same, and the potential there is the same, then the potential difference there is equal to this and that and that. They're all the same. All 3 points started at the same top of the river. All 3 points ended up at the bottom of the river. But all 3 have the same difference between top and bottom. So those potential differences are the same. Now for this particular point in the proof, if I had a capacitor that has area A and distance D, we would all know that there is a plus Q on one side and a minus Q on the other. And let's say what I did is I took an imaginary line and I wanted that ran down half of the circle. So I made semicircles. What would be the amount of charge on each of these plates? 1 Q over 2. So there would be a negative Q over 2, 2 sections, and two Q over 2s on the other. So these effectively add up to this. When you have capacitors in parallel, when you have these capacitors in parallel, it's a lot like when you combine and get the equivalent capacitance, that this new A equivalent is equal to A1 plus A2, that the areas add. So effectively, Q equivalent is equal to Q1 plus Q2. When you're dealing with capacitors in parallel, the charges add. So effectively, it's almost like we start like this, we draw our little dotted lines, and then the capacitors separate, but are still connected to effectively the same wire. So the charges add up. And if you've got that, we're going to use Q equals CV, or actually, since you guys are now being very OCD about this, Q equals C delta V. So this is C equivalent delta V equivalent equals C1 delta V1 and C2 delta V2. And what do we know about the potential differences? That they're all the same. And we're left with C equivalent equals C1 plus C2. So that is the equivalent capacitance for capacitors in parallel. And what you'll notice, the opposite of the resistors, yes. And so what I'm going to do is I'm going to put together, now it's just math, the reason why it ends up this way, math and physics. But if you had resistors and capacitors parallel in series, how I tend to remember it, I know for a fact that series resistors just add up. So Req is equal to R1 plus R2. And whenever you move from corner to corner on the square, you change the way the math works. Series parallel resistors, Req is equal to 1 over R1 plus 1 over R2 inverted. From there to there, capacitors in parallel, C equivalent equals C1 plus C2. And then series capacitors, C equivalent is equal to 1 over C1 plus 1 over C2 equivalent. And so what you get here from your observation, like if you want to remember how this goes, I just remember that series resistors add up and parallel capacitors add up as well. So series resistors add the same way as parallel capacitors. Parallel resistors add up the same way as series capacitors. So that's how that stuff works. Now, one last thing really that we need to cover is charging and discharging of circuits, and namely circuits that are RC. RC circuits are what we're looking at. Now, the way that our little RC circuit looks like is so this right here is a switch. Now, the mechanics of the switch aren't really that important, but what's happening here is when it's in the charging situation, the wire connects those two. When it's discharging, it removes the battery from the circuit, and the wire then connects those two. When it is in a charging situation, there is a battery, a capacitor, and a resistor. When it's in the discharging situation, that's closed, that's open, and you're left with just a capacitor and a resistor. Now, the equations that we use are for charging and discharging. And this is one of those things where initially I was like, as a student, I was thinking like, how am I supposed to remember? When you have two graphs on the horizontal axis, we have time. On the vertical axis, we have delta V across the capacitor. So we're looking at this. In one of the cases, our circuit looks like this. In the other case, our circuit looks like that. Now, obviously, the potential difference across the capacitor, when it's charging, increases as a function of time, so it looks like this. When it's discharging, it looks like this. So one of the things when you look at these equations, there's a derivation of it somewhere, and that derivation requires calculus, so we're going to stay out of that. So what I'm going to do is just talk about the macro picture of this. This dotted line right here is the potential difference across the battery. So if this was a 10-volt battery, then those V's right there are 10 volts. It plateaus at 10 volts. It comes down from 10 volts. And so one of the things, I think it, the those paddles that like when you shock the heart, you've seen those like medical dramas. I'm not sure. I've never actually been in the room where they do the paddles and then they go clear and pump it. But when they flip that switch, you hear that. Physically, what's happening is that those capacitors are building up a charge, and they are about to discharge through that person's heart. So in some cases, that it builds up in frequency and then it plateaus, but it still gets a little bit higher with time. It builds up, it kind of plateaus, but still gets a lot higher with time, or a little bit higher with time. For something like this, that the potential difference across the capacitor is this function, and we're going to get to that in a little bit. For discharging, the potential difference across that capacitor is V max e to the negative t over tau. So the biggest difference between a charging and discharging is instead of 1 minus e to the blah, it's just e to the blah, where that V max is the battery strength, or in the case of for our purposes in 214, all we're doing is just charging and discharging from the battery. Vmax is whatever you charge that capacitor up to, which frequently is just the potential difference of the battery. So for our purposes, it's this. Now, the question of tau and what it is called the time constant. And tau is equal to RC. That, yes,
Those equations for charging and one for discharging.
yes. The one for charging is on the left under the charging. One for discharging is under the discharging. That'd be cruel if I'd swap those out. But also, let's take a look at this, Sabrina. At the beginning of all these experiments, what's the value of t? I'll give you the easy one, and then I'm going to move over to the other one. What's at the beginning of the experiment, what's the value of time?
0.
0. Can you please say it in the form of an answer instead of a question? That would be nice. Thank you. So now, if time is 0, what's e to the negative t over tau if time is 0? 1. Well, you're just repeating because everybody else is saying e raised to the 0 is 1. So if e raised to the 0 is 1, the equation on the left becomes what? 0. So when you're first charging a capacitor, capacitor difference, potential difference is what?
1. 0.
Okay. Good plot. On the first one, you gave the right answer with the wrong attitude. Now you're giving the right attitude with the wrong answer. If e to the negative t over tau is 1, then 1 minus 1 is?
0.
Excellent. So the one on the left becomes 0, which means that the initial potential difference across a charging capacitor where time is 0 should be 0. A lot of times I looked at this as a student and said, how am I supposed to remember? Think about this. Time is 0. So e to the negative t over tau, where t is 0, becomes e to the 0. E to the 0 is 1. 1 minus 1 is 0. So when you initially charge a capacitor, the equation that you choose to be the charging equation should give you an answer of 0. The one on the right, e to the negative 0, is 1. So then it would be V max. That cannot be the charging equation. So that's the difference.
Dr. Eschenberg,
Yes.
you said that like with those like with the defibrillator paddles, that, it might, you know, it'll initially charge and then it might just keep charging a little bit.
Yeah.
I'm just looking at that graph. Could we say that it gets infinitely closer? To
It
that
does
line?
get infinitely closer. It would never reach that value, but it would get so effectively close to it that you just go, okay, fine, that's close enough.
But it never quite approaches it.
Correct.
Okay.
That's it. From a mathematical perspective, it would get within, like, I mean, you are correct. I could go into higher math, and then people's heads would, so for the safety of the group. And that's something that we'll cover right now. And what's interesting about this, and I'll leave it as an exercise for the class, the time constant, if t is time, what are the units of time? Seconds. So to get e to the 1, e to the 0, e to the 2, what must the units of tau be? It must be seconds as well. Because e to the negative 2 meters, it has to be a number. That exponential superscript has to be a number, which means the units have to go away. Much like coefficient of friction, you have to have a unitless value in there. So seconds are the units of the time constant. Ohms are the units of resistance, and farads are the units of capacitance, which begs the question, seriously, ohms times farads is seconds? Yes. Go and figure that out. I don't think I have it as a problem. It may be in there. I don't know. I don't think so. But you can get this from these two. Now let's say that we had a resistor of 20 mega ohms, a capacitor of 20, what would be the good, nanofarads, and a battery of 100 volts. First question, what is tau? So tau is just RC, 20 times 10 to the 6th, 20 times 10 to the negative 9. So tau should be 4 or 0.4. 0.4. So the time constant is 0.4. Now what we're going to do is we're going to use the charging equation, charging, and initially, see, I can't even spell initially barely. I don't expect you guys to either. Charging and initially uncharged capacitor plot delta VC as a function of time. So what we're going to do is we're going to plot this thing out and we're going to use the most sensible numbers that we can use. The time, 0.4, 0.8, all of these will be in seconds. 1.2, 1.6, and maybe if we have enough time or sanity left, 2. Now, there should be, it's understood, 0 and 0 as the initial point. Start our initial scale. 0, 0, 0.4, 0.8, 1.2, 1.6, and 2. So plotting this charging equation, V will be 100, or delta VC, 1 minus e to the negative t over 0.4. Now really what I'm doing is negative t over 0.4. 0.4 is the tau, which means 0.4 over 0.4 means that I'm dealing with e to the negative 1, then negative 2, then negative 3, negative 4, and negative 5. I'm stepping through this plot on intervals of the time constant. So at 0.4 seconds, it's 1 minus e to the negative 1 times 100. Let's see, I got to remember where this dang thing is. E to the negative 1. So I get 63.2 volts. For E, when time is 0.8 seconds, it's 1 minus e to the negative 2. I get 86.5 volts. E to the negative 3, where'd that come from? 95.0 volts. $98.2 volts. And then 99.3 volts. So you can see after a mere 2 seconds or 5 tau of time, we're at 99% of its charging capabilities. Yes?
So we started at -1 because it was uncharged from the...
It was, now originally time was 0 and delta VC was 0. What this is the multiple of tau. 0.4 seconds divided by 0.4 with the minus sign is -1.
Okay.
0.8 divided by 0.4 times negative is -2. So if we plot this out, 63, 86, 95, 98, 99, you get the plot that I drew out earlier. Now granted, the student who talked about it a few minutes ago is correct. It would never approach, it is approaching 100, but it would never reach 100. But effectively, after 5 tau, 5 units of tau time, you're at 99%, that's good enough. There's no need to go further than that because all it's going to do is get closer to 100 and never get there. We know that. Now, granted, if you said infinite time, and who has time for that? But it would then effectively get to that full battery charge. But if you're waiting to reach full charge, then that dude's dying because you never hit him with the paddles. Now, one of the things that is a problem that we do for problem sets, and some of them are in there now, is oh, I know. Hold on. I gotta make a note. Okay, good. So we charge a capacitor. We'll use the same thing as before. R is equal to 20 mega ohms. C is equal to 20 nanofarads. The potential of the battery is 100 volts. We definitely have a tau of 0.4. When does delta VC equal 70 volts? So when does it reach 70 volts? Well, it's somewhere between 0.4 and 0.8 seconds if you look at this. So the number that we should get is somewhere in the 0.5 range. But this is how we confirm it. The delta VC is the Vmax, or battery, 1 minus e to the negative t over tau. And this is how we do this alphabet soup style. We move this over here. Delta VC minus Vmax. Oh, that was the next step. Delta VC divided by Vmax. So the first thing you do is you divide, then you subtract the 1. To clean stuff up, we multiply everything by -1. And then, let me do it and then I'll explain it. So for this particular step, people go, what? What's going on? I took the natural log of both sides. Taking the natural log of an exponential function leaves only what I know, really, exponentials makes y'all sleepy. Oh, it leaves only what is in the superscript, whatever power is. So the natural log of e to the a leaves you a. The natural log and exponential cancel. And you're left with only, or they annihilate each other and you're left only with what is in the superscript. So that's how I go from there to there. I natural log that side, which gives me this. I natural log this side, which gives me this. I then multiply both sides by negative tau, and I get negative tau ln 1 minus delta Vc over Vmax is equal to time. So negative tau, negative 0.4. Natural log, 1 minus 70 over 100. Now, that should freak some people out that we may end up with negative time. But remember, the natural log function, when you take a natural log of something that's between 0 and 1, you get a negative number. So those negative signs will cancel. And I'm left with 0.48 seconds. And so that's pretty much what we assumed, between 0.4 and 0.8. So it worked. So taking the natural log of something, you need to know how that works, because when you do your equations for the problem set, that's what you got to do. All right. That is effectively everything that we need to know for test 1. What I'm going to do now is talk about, someone brought this up, and it was this particular problem. What I'll do is I won't do this problem as is in the problem set, but what I'm going to do is I'm just going to say all the resistors here are 10 ohms, and the goal, this particular problem is, give me the potential at A and at B, and do it in the quick and dirty way. Well, what you need to do, obviously, the first thing you need to do is, and let's just say we have a 100-volt battery in, and we need to understand the true definition of equivalent resistor. And REQ can replace its component resistors and the behavior outside of that equivalent resistance will not change. So what we have here is we have two unusual blocks of resistors. Now in this one, the triangle initially becomes like this. Where that's 20 and that's 10. And then this first block, which I'll call RL for left, is 1 over 20 plus 1 over 10. How did the resistors do what?
How did the 3 become 2? Like the 3 in the triangle.
Initially what I did is the first smooshing is that these two resistors are each 10 ohms. They're in series. They become 20. So this becomes 6 2/3 or 20/3 volts. The one on the right, you can immediately smoosh that one down. 1/10 plus 1/10 plus 1/10 inverted. And that gives you 10/3. So R equivalent is equal to 20/3 plus 10 plus 10/3, which works out nicely because it's 20 ohms. So really the first thing was to figure out the equivalent resistance of this thing. The next part would be to find the current flowing through the battery. 100 volts divided by 20 ohms is 5 amps. And one of the things that I will promise you on the test is the numbers will work out quite nicely. If you know how in the problem set it was like 135 over 291, it's not going to be that way on the test. It will be multiple. It will either be whole numbers or fractions, like 1/2, 1/3, 1/4, 1/5, and that's about it. That's as complex as I'm going to make it. So if you're ending up with very, very strange fractions, something's gone wrong. There is no difference between that circuit and this circuit excuse me, with respect to determining A and B. A lot of times what I do when figuring out potentials in the middle of circuits is when I go through this, and when you look through the notes, you see a whole page of me swooshing down resistors into more simple and more simple and more simple patterns. And there typically is something that looks like this somewhere in the middle. And while I'm doing the problem, I am writing down every single fraction I get because I want to look at VA and VB and find it real fast. Let's just put grounds right there. For the left resistor, 100 minus VA over RL is equal to I naught. The current running through the whole thing is the same current total that's running through RL and R in the middle and R sub R on the right. I know what these two are, so 100 minus VA is equal to I naught RL. So 100 minus I naught RL is equal to VA. So 100 minus 20 times 20/3. Whoa, did that mess up? Oh, I'm sorry. Thank you. Oh, thank God for that. I was about to end up with a negative number. That would have been very embarrassing. So 66 2/3 or 200 thirds of a volt. Now for the other way to get VB, probably the fastest way would just be VA minus I naught R, so 200 thirds minus the drop across that R, 5 times 10 is 50 thirds. Did I get that right? Yes? Okay, good. Sometimes I gunsling the numbers in my head. And that's VB. But another way that you could do it is 0 plus I naught R sub R, which is 5 times 10 thirds, which again gives you 50 thirds. It also shows you the benefit of why you should keep it in fractions. Because when I step down to 50 thirds and I step up again to 50 thirds and they're both identical, I have high confidence that this thing is working. If you're sitting there rounding stuff and coming down you've got 16.5 and coming up you've got 16.9 or whatever, then you do have a certain amount of uncertainty involved. Yes?
Can you put up the original circuit for me? So if you wanted the potential on like the resistor set to the right on the very top, would then you have to use a different current other than I naught?
So we're talking about the potential difference across there.
Yes.
Now, for a potential difference across there, these wires are all connected. So they're all at ground. These wires are all connected, so it's potential at B. So the potential difference across that resistor is VB minus ground, or just VB. Now, if you wanted just the current, one of the things that I like, one of the things that I get out of determining VA and VB, suddenly all the currents become very easy to determine. The current across that resistor is simply VB divided by R. That one thing. I know the high voltage, the low voltage, I know the resistance, bam, I got the current. So you can do this many different ways. It just, you develop a sense of, oh, I've seen this pattern before. I'm going to find all my V's first. Other times, you can't really, in more complex circuits, you can't really do this. But in simple test problems, hint, hint, you can.
And all those currents across that particular thing should equal the I naught current.
Yeah. If you added the currents for there, and there, add up those three, you will get I naught. All right. So really, we're down to 9 minutes, which isn't enough to talk about test 4. Take a look at test 4. We'll go over that on Tuesday. Test is 1 week from today. Thank you.